Okay, hello everyone. So in this video I wanted to discuss a problem related to dynamic programming optimization. So the agenda for this video is to go through a TP problem. Uh, it is a Codeforces problem, and I want to discuss the entire steps that are needed to solve the problem in optimized fashion. So we'll go through the brute force solution, we'll find out the recurrence relations and find out some patterns in them, use appropriate data structures and algorithms, and finally arrive at an optimal solution. So let's begin. So this is the problem from Codeforces, so let's go over it. So you're given an array of n integers, and let's consider S as a set of segments satisfying the conditions given below. So each element of S should be of the form x comma y, which is a pair. Each of them are between 1 and n, and the first is less than equals to the second. So no two segments in S intersect each other, so that is the second condition. Third one is that the sum of array elements in that range is greater than equals to 0. So they're also defining the length as the number of integers between them. So length of x comma y is y minus x plus 1. They're defining a function f of s defined as the sum of lengths of every element in S. So this is the function that they have defined, and they are asking what is the maximum value of f of s among all possible s, and the constraints are as follows. So let's go over the samples. So in this case we want to select, so 3 minus 3 can be valid, and minus, if you take minus 2 it will be minus 2, and if you take 5 then it will be 3. So the first 4 elements have sum 3, hence it is a valid range, hence this range can be taken. So 3 index 1 2 3 4 can form a range, this cannot form, so hence the answer is 4. In the second case they have mentioned that the sum of the first 9 elements is non-negative, hence the answer is 9 here. And for the third case, there is all the elements are less than 0, so we cannot take any range in S, and they have mentioned that the value of the function for an empty S is 0, hence the answer is 0. So this is the problem. So let's proceed. So this is the diagram. If we consider any arbitrary array A, and if we try to find out all the subsets S, so for the first array, let these green lines denote the ranges that we want to select, and they have some 0. So as you can see, there can be exponentially many choices to make. So this is the first observation that we can observe. Let's say all the array elements are 0. In that case, there can be so many choices to consider, and it is not optimal to go over all of them. So this is the observation. So let's try to represent the problem mathematically. In one line, if I had to state the problem, it is finding maximum sum of lengths of disjoint subarrays each having sum greater than equals to 0. So this is the problem statement in one line. As they mentioned in the statement, we are stating this: S is a set of disjoint subarrays to be considered, each subarray having sum greater than equals to 0. And as they have mentioned this function, so f of s is the sum over lengths of all the ranges that are present in S, and we need to find the maximum value of f of s over all possible sets S. So this is the mathematical representation of the given problem. So let's make some observations. As we observed from the images of valid choices for our set S, we can observe that there are exponentially many choices to make for the set S. So let's start with recursive brute force solution. So let's try and come up with a simplest non-optimal solution that we can think of, which is a recursive brute force solution. So to start with that, we will start constructing our set S, which is a subset of subarrays, right? So we start at index 1, and there are basically two choices. If we are going to consider the value at index 1 in any subarray, or if we are not going to consider it in any subarray. So I've listed down the choices at each point I. So there are basically two choices: either take the subarray starting at index I, and if you're going to start it at index I, it can end at any index j which is greater than equals to I, and the condition is that the sum must be greater than equals to 0. Other option is don't take this element in a subarray. If you are not taking it in any subarray, we are moving on to the next index that is available, which is I plus 1. So this is the basic brute force recursive approach for this. Now let's try to implement it. So I have written a function go, which is going to compute the answer for us, and finally we are going to print the answer if since we are starting at index 1. So we are calling the go function with index I equals to 1. So let's go over the function one by one. So the first choice that we considered in the previous slide, we are not going to consider AI in any subarray. If we are not going to consider it, we are moving on to the index I plus 1. Okay, so the second choice was to consider it in a subarray. If that is the case, the subarray sum must be greater than equals to 0. And one more thing that I wanted to mention is assume A is a prefix sum subarray, so that we can calculate subarray sums in constant time. So we are going over all the possible j's in the range I to n, and for all of them we are going to maximize our answer, and j minus I plus 1 is the length of the subarray that we are considering. And if we are going to stop the subarray at j, we need to move to the next index j plus 1. So this is how we are considering the two choices for each index I, and I've also written down the base conditions, and the answer will be written from this function. So this is the implementation for recursive brute force approach, and the time complexity for this will be exponential, because at each point we are having two choices and the branches will exponentially increase, similar to a Fibonacci pattern. Next, what we can do to optimize this is introduce memoization. So we are keeping the same function, just we are introducing these three lines. We are introducing a new array dp, which is initially filled with -1, and we are just checking if it is not -1, it means it is already computed, and we can simply return the answer from there. Otherwise, we need to compute the answer by following the code below, which is same from the previous slide, and this will reduce the time complexity to O of n square. So this approach that we implemented will be, the full time complexity will be O of n square, because the number of values that index I as a state can take is up to n, and for each state there are n iterations, so overall time complexity will be O of n square. Okay, so let's try to jump from the recursive to iterative approach, and try to find out the recurrence relations from our uh, recursive function. So let's define dpi as the best answer we can find until index I. Okay, so we can see that dp of I will be the maximum value we can take over two choices. So the second one is not considering ith element in any subarray, and the first one is considering ith element in a subarray starting at index j, which is less than equals to I. Since we are computing dp from left to right, we need to move from left to right while computing the states of dp. And the condition that the sum of elements between I to j is greater than equals to 0. So this is the recurrence relation that we have derived from our previous function that we have written. So simply the first choice is considering it in a subarray, and second one it is not considering in any subarray. So now I'm also stating the base condition as dp of 0 equals to 0, since for index 0 we don't have any element present in the array, and our final answer will be stored in the nth element of the dp array. So this will be the recurrence relations, and we are going to optimize or find patterns in this only, so make sure it is clear. You can take your time to understand it. So if we have to just go through it, so we can see that in recursive function we are going to the next index, but in the recurrence relation we are basically computing from left to right. So we need to take the values from the TP array where it is already computed. So left part of the array ith index will be already computed, so basically the left to right part will be handled, and the valid values will be stored there. And in this part also this is the length, and this is the next index where the subarray ends. So you can see if you're considering the subarray from j to I, then the previous index to the j will be j minus 1, hence we need to get the answer up to index j minus 1, get the length from j to I, and update the answer for the ith index of our TP. So let's try to simplify the relation now. So this is what we came up with in the previous slide. Now basically we can denote the sum of elements from I to j by introducing prefix sums. So let's say prefix of I denotes the sum of the first I elements of the array. Then the sum from j to I can be denoted by the sum of the first I elements by the minus the sum of the first j minus 1th elements. So this is easy to observe and trivial. So now the relation becomes as follows. This condition, sum of ai is greater than equals to 0, will be replaced by prefix of I minus prefix of j minus 1 greater than equals to 0. And if we rearrange it, we get this. Prefix of I is greater than equals to prefix of j minus 1. So we eliminated the factor of a and introduced prefix array and arrived at this condition. Let's move forward. This is what we arrived at, and let's try to implement it in an iterative fashion. So this is the entire code, and our final answer will be stored in dp of n. So we are taking the input, we are immediately converting array a into a prefix array. So instead of saying this is pref, a becomes the pref, because we are not going to need a later on, so it's better to convert it into a prefix array immediately. Similar to the recurrence relation, we are first of all we are converting the a into prefix array. We are considering the first choice, which is not considering ith element in any subarray. So if you're not considering in any subarray, the best answer we can find out is taking from the ith minus 1th element. And the second choice is going over all the choices for taking ai in a subarray, and here we are checking that the sum is greater than or equals to 0. So this condition will be same as transferring this term to the right hand side and the term that we have arrived on the third line. So we are updating dp accordingly as denoted here, and the final answer will be stored in the nth element as I mentioned before. So this will be the approach that we arrive at currently. Let's try and find out some more insights from the recurrence relation. So this is what we arrived at. Next, what we can do is um, just rearrange this g minus 1 by separating out the negative sign. And if you can see that length of subarray from I to j will be I minus of j minus 1, which is equals to the number of cells that are present in the range I to j. So we can basically rearrange the equation as follows. And I is independent of j in this equation, right, the first term. So we can basically remove it. And one more thing to observe is this j minus 1 and j minus 1 will be common. So basically the value that is present in the max term is singular value for a singular index. So so in this step we took I to the front, which is independent of j for the maximum function. We rearrange the length terms, and basically in the next step we are going to replace j minus 1 by some index id, right? So j minus 1 can be replaced with some index id, and now id will be less than I, because j minus I is less than equals to I. Now id becomes less than I, and obviously the conditions are still present, that prefix of I is greater than equals to prefix of id. And now we have removed the dependency on j minus 1 and called it a separate index id. So as you can see, this recurrence relation is in one variable form now, because this term, so basically for computing the value of dp of I is a constant, and this max term is only dependent on the variable id, not I or other dependents, and dp of I minus 1 can be computed in constant time also. So we can say that this recurrence is in one variable form now. So let's try to optimize it further. So as you can see, we are finding the maximum value from all the previous indexes to I over the condition that prefix of I is greater than or equal to prefix of id, and with that condition we are finding out the maximum value of dp of id minus id. So instead of going through all that, we need to store this value for all indexes and use it for computation later. So this term is the same as term taken from the maximum equation here. So let's try to go over the next point. Since we are going to iterate over all the prefixes with prefix id less than equals to prefix of I, and the condition that we derived in the previous slide, where we need to store these values in some data structure so that we can retrieve it efficiently. So we need to iterate over all of these values which are less than equals to I, and over all of them we need to find the maximum value of the second term here. So let's store it in some data structure such that the keys will be prefix of I and the values will be dp of I minus I, and let's try to implement it now. And basically once we have completed the dp of I, then we need to again push that key and corresponding key and value into our data structure so that it will be used for the later indices. Okay, so let's try and go over the implementation for this approach. I'm using a pair of int comma int as a data structure, so I'm calling it my data structure, and we need to handle a base condition 0, 0 that we mentioned while computing the recurrence relation. um, that is the part we are using pair of int comma int as a data structure, as a key value data structure. Here we are converting array into prefix array, and this is the first choice. So in the previous slide, so this is the first choice, I plus maximum of this. So the value to the left of the comma is the first choice and right one is the second choice. So the first choice is to take the best value over all the keys which are less than equals to a of I. A of I is our prefix array, and update our dp of I with the best value for the corresponding key that we found out from this slide, right? So this is the first choice, this is how we will compute it, and the second choice will be straightforward, taking maximum with the previous index, and after that we need to store the key and value into a data structure so that for the letter indices it will be used to update the dp array, and finally our answer will be stored in the nth element of the dp. So this is the best approach we can think of. So let's try and optimize it further. So if you observe clearly, this is the for loop we need to get rid of, right? So let's try and find out what are some of the ways that we can do it. So if you notice that we are iterating over all the keys below a of I, so that is basically the range minus infinity to a of I, anything that is below a of I, as you can see in this highlighted code. We are iterating over all the keys in our data structure which are less than equals to a of I and finding the maximum value of that value corresponding with that key. So how we can improvise this code is the next question. So obviously we need some data structure that can give the maximum value in that range quickly and also support adding of the keys. Both operations should be equivalently faster. So the data structure that we can think of is segment trees, obviously, because segment trees support point updates and range queries both in logarithmic time. So in this specific problem I used implicit segment trees because the keys that we are going to update in our data structures can be very large, up to the power 10 raised to 9 or 10 raised to 15 or even negative. So basic segment tree won't be able to handle that case. So that's why I'm using implicit segment trees, and the only difference between implicit segment trees is that it can support arbitrarily large indices by having dynamic nodes. So in the next slide I want to explain a little bit about implicit segment trees. So this is the structure for node of implicit segment tree. We want to store the maximum value, and there are basically two pointers left and right for each node which are not initialized uh, at the start of initializing a segment tree. So initially both of them are null. As you can see, this is the constructor for the node, and let's see how we will perform the updates and queries on this. So this is the function update. Basically we are going to update the root of the segment tree, and updating will return a node pointer to us. So after performing the update in the segment tree, it will return a new root which is the accumulation of the update. So the way we read this is a node stores the maximum value in the range L to R and we need to update the index id with value. This is the way we read it. So this recursive function will go through all the ranges, or basically all the ranges that has the index id in them. So if L2R consists of the point id, then this recursive function will basically arrive at that instance. And if it is arrived at that instance, we need to update the maximum value for that. So let's try to go through this. So basically we divide it into two parts, the left half and the right half. As you can see, if the null is not present and we need to update the index at that position, we create a new node. So this is how dynamic segment trees or implicit segment trees work. So dynamically, those indices or those ranges will be generated at runtime, so that not necessarily the whole segment tree is constructed while initializing it, but depending on what values it is storing, it is initializing it at runtime. So we need to update the left point. The left node will store the maximum from L to mid, and the right node will store the maximum from mid to +1 to R, and we need to update the value id with value. And finally we'll retain this node pointer, so that basically these updates happen. So this is how the update function works. Next, if you want to query for a range, so um, again, the root of the segment tree or any node of the segment tree stores the maximum from TL to TR, and we want to find the maximum from QL to QR. So this is the function that we write if the ranges don't overlap. mm, this is not the valid range that we want to look up, so basically we return from that. If the node completely lies in our query range, we need to update the best maximum that we can, like this the answer for this query. As you can see, this is a void function, and it doesn't return directly the maximum value in that range, so we need to keep a global variable that will be updated each instance this function. We also need to reset it before calling this function, and we can update the maximum here. Again, the standard part, we divide the range into two parts and get the maximum from the left half and the right half. And as you can see, while querying, we only need to query where the nodes are present, so that is why we are considering left is not equals to null, so that we are iterating over the nodes that are created, and if they are not created, means there is nothing in that range. So this is how the query function will work. So for the initialization part of implicit segment tree, for this is only valid for this problem. We are introducing a term offset. I will explain it in some time. We are introducing a term infinity as 10 to 16. This is how you initialize the implicit segmented node. So the root node will call all the functions, all the updates and queries over this root node only. And if you want to perform an update, we can say that the root node stores the maximum from 0 to infinity, and I want to tell it that go put this value against this key. So this is id, this is value. So this is the point update that we are performing. Update this index with this value. So this is how we read it, and as you can see, this value can be negative, but we are saying that root of the node stores values from 0 to infinity. But if this is negative, the updates won't be performed. That's why we are introducing a term offset, so that even if this is negative, we are adding a sufficiently large positive value to it, so that it will be always positive. So this offset will be only added for a of I, which is our prefix array, and these values can be anything: large, negative, positive, anything. Just the keys need to be in the range of the node range supported for that node. So root stores the maximum from 0 to infinity, and we are asking it to update this index with this value. And if you want to get the maximum, we are asking it that the root consists the maximum from 0 to infinity. Now give me the maximum from 0 to ai plus offset range. So this is the query left, query right is this. As I've explained here, that wherever ai is present, we need to add offset, because we are shifting the negative values to the positive values by the same amount, so that it is supported by the implicit segment tree indices. So again, we use offset to make sure the query ranges for the segment tree are greater than equals to 0. So that part. So the workflow that we arrived was, so basically we first wrote a brute force recursive solution, then we derived the recurrence relation from it, and we found out some patterns, and basically optimized those patterns or those naive loops using some data structure, in our case segment trees, and finally arrive at implementation. So let's go over the final code. Okay, so this is the accepted code for this problem using implicit segment tree. I will also discuss the better solution without this implicit segment tree if it's unclear. So these are our constants: ai array, which will be later converted to prefix, then dp, and the best maximum that we need for getting the maximum values in a particular range. Basically the query answers will be stored in best mx. So the node will consist of the maximum value, left pointer, right pointer, initialized both with null initially. We went through this update function earlier, which is as it is, no changes. Get max function, best max, the answer for this maximum will be stored in best mx, which is a global variable defined here. And this is the overall structure for a implicit segmented node. We are initializing the root here. We are initializing the root with a new node offset, and now we need to put our base condition, which is 0, 0. And basically whenever we are using any index in implicit segment tree, we are going to add an offset to it. So this is the standard stuff that we discussed earlier. So now let's compute the dp array from left to right. We are inputting a of I, converting it immediately to prefix array. So instead of using any other array pref of I, we are simply changing it in place. So prefix array is now a of I. So before getting the maximum, as I mentioned, we need to reset our best maximum, because it may be filled with previous query value. So we are resetting it. We are calling the getMax function. We need to get the maximum from 0 to ai. So this is the function that we need to, this is the parameters that we need to call the getMax function with, and update our first choice, which is I plus the best maximum, which was the for loop that we saw initially. So this best maximum will be acquired from this. The second choice was don't take a of I in any subarray. So if we don't take it, we can simply update the answer from the previous index. And after that, we need to put this key with and this value into our data structure. So we are going to basically update e of I comma dp of I minus I, so that it will be used for the later iterations. And again, so wherever a of I is used, we added offset so that this negative index does not occur. So this was the overall solution. Final answer will be stored in the nth value of the dp. Okay, so if this solution was a little bit complex, and so let's try and go over a better solution if it's possible. So I want to present a solution which is without using implicit segment trees. So as you can observe that the prefix array, its use is only to check which values are smaller or larger, right? So we are not using it as a cost function in any dp index or anything. We are just using it to compare which for indices which values are smaller or larger. So we don't need to store those large keys, right? So what we can do is use coordinate compression. So let's say our prefix array contains 3 terms: 10 raised to 9, 10 raised to 10, 10 raised to 12. But the only thing that matters to us is whether prefix of I is less than or equals to prefix of j. So it doesn't matter those values are arbitrarily large, we can map them to a smaller values. So 10 raised to 9 will be mapped to 1, 10 raised to 10 will be mapped to 2, 10 raised to 11 will be mapped to 3. And still that greater than or less than conditions are valid. So this is the basic idea behind coordinate compression. So basically we compress the prefix values in the range 1 to n. So if there are n unique values, they can be compressed in the range from 1 to n or 0 to n minus 1, depending on the convenience that we use. So, and if the values for those keys are between 1 to n, we can simply use segment trees or fan vectors. So let's go through the better solution. So instead of implicit segment trees, I'm using a binary index tree or fan vector in this case. This is the size, this is the values that the segment fan vector stores, initialized all with minus infinity. This function will update the index id with value. This function will return the maximum value for the range 0 to idx. So this is prefix max up till index idx. So it will return the maximum. So this is the basic structure for binary index tree. Overall, the initialization is same, converting a of array into prefix array. Now the thing is to map those large values into a smaller, which is 100. So to handle the base condition, I have used the 0, 0 also, because we need to update in our data structure dp of 0 with 0. So I've pushed all the values of prefix array in the vector b. I've sorted it, and whenever I want to update or query particular key, instead of calling it with directly a key, I am calling this index of function. So wherever I want to get the prefix max or update the max, I am calling this index of function. So let's go over what this index of function is going to return. So as we have arrived at this part, all the prefix values will be stored in b. We are going, if you want to find the index of this value, we are going to find at what position that value is present in array b, and we can assure that all the keys are already present in the vector b, because these are prefix values, these are prefix values, these are prefix value which are already pushed in b. So we are never going to call this index of function with a value that is not present in b. So this is the assertion for that, and basically convert it into one best indexing. So this idx will return 0 best indexing of value passed as a parameter in the array b. That way we are converting those large keys into a smaller, which is 1 to n range. And this part remains the same, choice 1, updating with best max. As you can see in this submission, choice 1 updating with best max. This part is handled by a fan vector now. And the choice 2 is a simple constant operation. Just take the value from the previous index and update the dp of I. And for performing the update, we want to update this key with this value, as we saw in this solution also, this key with this value. In this case we had to use an offset. In this case we just using the index of function so that the keys are smaller. And finally our answer will be stored in the nth variable. So this is a bit simpler approach, but it requires you to know coordinate compression and the technique used for that. So this was the final solution. I might say the best and most optimal solution, because as you can see, the time required for this is literally 78 milliseconds and this is 343. So as you can see, this is literally recursive solution and involves a lot of initializations and dynamically creating new pointers and memory, and the overall recursive approach is going to take some time. So this time time taken is justified using this. So, when victory is literally iterative and uses less memory. So this was the final solution, and the code comparison that I wanted to do was, so this part is literally everything remains same, right? So as you can see, uh, updating the base condition 0, 0 is done here, just replacing it with the corresponding functions for find victory. Prefix array computation remains the same, which is handled here. Choice 1 and choice 2, literally the same code, just difference in how best mx is computed. So best mx is computing by calling the root here from 0 to ai, and here it is calling the prefix maximum for the compressed key for a of I. Overall, no, no, not much changes, just a little bit faster approach and easier to understand. So that was all for this video. So if you like the video, you can go and follow me on LinkedIn, GitHub or Twitter on these links, and I can share for more content like this. Okay, and subscribe for more such videos. Thank you.